Now, sometimes we will have some roots that are not perfect squares or perfect cubed roots. For example, in E, we are asked to simplify e to the square root of 90. And there's two ways we can do this. If you can recognize two factors that multiply to give us 90 and one of them to be a perfect square, like 9 times 10, we could split them up and say, okay, the square root of 9 is 3, and then we'll leave the square root of 10 because 10 is not a perfect square. And also, there are no other factors of 10 that would be a perfect square. Another way to do it, and I can do it here in green, is if we took that number 90 and we did a factor tree. We could do, let's see, 2 times 45. 45 would be 5 times 9. 9, we would have 3 times 3. Because our n equals 2, we would look for a pair. Well, we have a pair of 3's. If we have a pair of 3's, then that 3 can come out of that index because we have found a 3 squared. But this 2 and this 5 do not have pairs, so they have to stay in. 2 times 5, and that would give us that 3 radical 10. For looking in F, the fourth root of 144, so let's see what happens with 144, because I don't know my perfect fourths. I know my perfect squares and maybe a few perfect cubes, but I don't know my perfect fourths. So let's do a factor tree. So we have them all there. Notice we have an n of 4. So we're looking for 4 of a kind. Well, I have 4 2's, and they don't have to be in a row. You may have started with 8 and 9, and then you can go from there. 8 and 9, sorry. What is that? 16 and 9. But we found that entire prime factorization, we have 4 2's, so that 2 can come out. But we have 2 3's. We don't have enough of those 3's, so those 2 3's have to stay in. We needed 4. So we end up with 2 square root of 9. When solving equations that involve those radicals, those roots, we want to be sure and check that the solutions work because we can come up with extraneous solutions, basically extra solutions. So in example G, we can add 7 to both sides. That leaves us with the square root of 3x minus 2 equals 7. Remember the index is 2. So in order to get rid of that square root, remember we're trying to get x by itself, we're going to square it. Just like if we have addition, we're going to do the subtraction. If we have multiplication, we're going to do division. If you have a radical of index n, we're going to take it to the exponent of that n. But if we do it to the left, we must do it to the right. So that's going to leave us with just the radicand on the left-hand side equals 49. If we add 2 to both sides, that's going to give us a 51. Divide both sides by 3, and we get x is, I believe, 17. We do want to check it. If we put in 3 times 17 minus 2 under the radical, and that minus 7 is outside the radical, be sure that you are intentional with your writing and you don't accidentally write things outside of the radical or inside of the radical when they're not supposed to be. And then we get 7 minus 7, which does in fact equal 0, so it checks. In H, we still need to isolate that radical, so we're going to subtract 1 from both sides. Now, at this point, we could stop, right? Because a square root cannot equal a negative number in the real number system. But sometimes we don't catch that. So we're going to square both sides just to see what happens. We're left with 3x minus 20 equals a positive 1. Add 20 to both sides, we get 21, and we get an x equals 7. Notice if we plug in that 7, however. Can't spell the word check. There we go. We get the square root of 3 times 7 minus 20 plus 1 equals 0. And we need to make sure that that works. 1 plus 1 does not equal 0. So there is no solution.